Hello everyone, this is me again, Assam Helmi. I'm a petroleum engineer. I graduated from South University in Egypt in 2020. Before we start our webinar today, I would like to give you a short presentation about Reservoir Solutions company. So this is our company profile. Reservoir Solutions is a company specialized in providing technical studies and courses for the oil and gas companies and professionals. The company incorporates many professionals with diverse technical background related to the oil and gas exploration and production. Some of our services include the technical reservoir studies, field development plans, FDP, reservoir static and dynamic modeling. By the way, we are working in these days on one of these courses, which is reservoir static and dynamic modeling. We also provide economic feasibility studies, technical support for academic researchers, master and PhD students. We assist in writing technical papers and publishments. We provide also technical petroleum courses, and we will mention one of our upcoming courses in the next slide. We also provide mentorship programs. If you have a project and you need assistance working on these programs, and we provide mentorship programs to help you reach to the results that you wish. Before we start our webinar, I would like to introduce one of our upcoming courses, which is titled Cased Hole and Production Logging. This is a 7-day course, every day for 3 hours. And this course is specialized for both professionals and for the university students who are willing to get more knowledge on this topic. I will give you more details about the course, but I will also tell you in the beginning when this course starts. This course will start in 2 weeks from now. It will be in 20th of March. So we are separated by 15 days before the start of this course. I will provide you with a link to apply for this course and also for the file that contains the contents of this course, day-by-day content. So let me share the, yes, this is the content for the cased hole and production logging course. By attending this course, you will enjoy lifetime access for the recordings of the 7 days. You will also have open discussion with the instructor during the whole course. We also provide you with online certification. By the end of this course, you will be able to understand the theory and application of the production logging tools, different tools, design the BLT logging job program, and other points also. You will be able to select the optimal application mode for RST log. We provide in this file the content for each day, 7 days. I will mention some of the titles that will be discussed in the different days. For example, in day 1, we will give an introduction about the course, the applications, different applications of the production logging tools. For example, in day 4, we will cover software practice that be used in the production logging. For example, in day 5, also software practice, single phase example, multi-phase example for the oil producer wells, and also for gas condensate wells. For day 6, analysis behind casing, what is weight, why ABC, and different applications. And for the last day of the course, we'll be covering the pulsed neutron tool. So these are the contents for the course. I will provide you in the chat by the link on how to apply for this course, and also the content of the course that I'm sharing with you right now. So it's shared with you in the chat. Back again to my presentation. So it's a time to introduce our instructor for today's webinar. Our instructor is Engineer Eugene. He is a co-founder of Avalon International Corporation and a petroleum engineer at Kansas Geological Survey, KGS. Eugene has worked for 5 years at Plains CO2 reduction partnership before transitioning into KGS, which I told you now, Kansas Geological Survey. He managed several research and field scale projects funded by Department of Energy, including Wellington Field CO2, EOR, and storage pilot. He is currently serving as a joint PI for Carbon Safe Phase 2 Integrated Mid-Continent Stacked Carbon Storage Hub project. Eugene is specializing in reservoir modeling, simulation, and fluid geochemistry applied to the oil and gas reservoirs and waste fluid injection. There is more to tell you about Engineer Eugene. He's very familiar with the UIC program, including hands-on experience with the UIC class VI, well permitting and preparing projects to qualify for 45U credits. Eugene is also interested in space exploration and developments in advanced life support systems for space settlements. He is continuing research and publication activities in this area. So I will give you some rules before we start our webinar. Kindly, if you have a question regarding whatever point in the webinar, please put your question in the chat area, and please keep the chat area clear so that I will read your questions to our guest speaker today to get your answer. We are keeping the mics muted and the camera also, so that you are not interrupted by the others. For the certification for attending this webinar, we will send a link for getting a certificate in the chat area by the end of the session today. By the way, this session is planned to last for almost 1 hour, including the questions part. I will provide you with the links for our social media platforms, Telegram channel, and YouTube, and others in the chat area. I will send it shortly. And here's also our email. You can reach to us by texting us on this WhatsApp number or by emailing us on this email. So Engineer Eugene, thanks for joining us for today. Thanks for your time, and the mic is yours.
Thank you for your kind introduction. Let me share my slides. I hope everyone can hear me fine. If not, please let me know. So I will be speaking today about sort of fundamentals of carbon capture, utilization, and storage. I think I'm experienced enough to talk about this area. It is new and upcoming, but already it has seen a lot of investment from large companies. There are also some startups that are interested in this area in the United States and all across the globe. There are kind of several aspects to this. So as you can see, there's capture. So you need to capture carbon in order to be able to do anything with this. And there are utilization and storage. So we'll talk about some aspects of utilization, since this is reservoir studies and reservoir related activities, but we'll also talk about storage. And in recent years, there's a trend that especially in the United States, maybe in other areas it would be a little bit different, and you'll see why it applies to the United States more. The storage component is actually becoming more popular than the utilization or EOR, enhanced oil recovery technique. Also, there's another aspect to that that needs to be discussed, but probably not in today's little course, that the utilization is also being broadening up, because now there are lots of things that different companies are attempting to produce from CO2, including things like methanol and other fuels, but also trying to turn CO2 into different kind of products that you can use in manufacturing. And so this is a very exciting area to be. It is definitely coming from research or research and development domain into commercial space right now. And you will see more and more projects popping up here and there, and they will all have kind of very, very different take on this, depending on the rules of rules of engagement in each area. I will tell you about the area where I know how things work, and I know mid-continent United States. I will be talking primarily about Kansas, and you will see primarily you will see examples from the work that I've done at Kansas Geological Survey. With that, here's my brief thanks for previous introduction. I also brought in some of my introduction here. The other thing you need to know is that I transitioned from Kansas Geological Survey, and I work for Energy Innovation Center in Wyoming, University of Wyoming. So it's a new position, brand new position for me. In a different capacity. I will be working on hydrogen. I will be directing Hydrogen Center in Wyoming. So as mentioned, I worked on a number of projects. Some of them are pilot scale, some of them are characterization studies. Some of the projects that are currently going on are actually industry related, related to deployment in the field at the moment. And probably you have seen those diagrams before. Let me see if I can maybe move it a little bit somehow, somewhere. But anyway, so you probably have seen those diagrams before. You know, you can find them in Wikipedia and everywhere on the web. But I think they're still good, a good illustration to kind of show to people who are unfamiliar with the concept. So we are basically condensing CO2, we're pressurizing CO2 and also heating it up so that CO2 can reach a supercritical point. So in this point in the diagram, so in this diagram, you see that here's the pressure, here's temperature, and you need to get CO2 to certain pressure and temperature so it gets to a supercritical state. You can also do it in a liquid state. And one of our projects actually did inject CO2 in a liquid state. There's nothing that prevents you from doing this, but the supercritical fluid is more preferable. The reason to do this is to decrease the volume. So this is for one. So you see that the volume is decreasing with the pressure applied to this fluid, and temperature also makes it move to the supercritical region. Also, it behaves a little bit differently, and if you are injecting in a uniform supercritical fluid state, you will have less problems actually delivering fluid from the surface to the reservoir, which is pressurized. You can basically how you do this. What the concept of storing CO2 underground is either you move this fluid to move other fluids like oil, like in this case in this diagram of enhanced oil recovery, where you inject CO2, it becomes miscible with oil. It pushes oil to your producer, and you get back some of that CO2, but also oil that you otherwise cannot sweep from the reservoir. Usually it applies sort of to a tertiary. It is a tertiary recovery method, so it can be applied and more beneficial for the reservoir only after you have done your primary recovery, basically recovery before you do any sort of stimulation. Then you can do the water flooding, basically applying pressure to your left the oil that is left in the reservoir. But after that, you cannot push oil without any additional help. And in this case, the CO2 bank can help us sweep that kind of residual oil in the reservoir, make sure that it's miscible, make sure it moves throughout the reservoir and moves to the producer. Or you can just inject CO2 and leave it there if you want to basically help the climate change, and if you want to keep the CO2, keep the product underground. And the reason for those two methods is obvious. CO2 EOR is definitely can be profitable if the project is organized right. Yes, you can make the profit, but if you are talking about the grand scale of CO2 that needs to be sequestered, stored underground, you are talking about gigatons, and I'm not sure if all oil fields all around the world can actually accommodate all of the CO2 that needs to be captured and sequestered. So that therefore you might use some of that CO2 for enhanced oil recovery in the projects that you think could be economical, and the rest of that you can basically store in saline aquifers, hopefully forever. So again, if you are talking about enhanced oil recovery, there are certain characteristics that apply to the reservoirs where you can, some feasibility. There is some feasibility to apply CO2 to those reservoirs, and you can get back some of that oil that is residual. So basically, the criteria are the depth, the pressure, and again, this is a function of temperature and pressure. Certain pressure is more favorable than some other, and this is due to miscibility of oil. That number actually could be higher, but preferable in this range. This is the most kind of applicable to most of the reservoirs. Permeability needs to be high enough, and oil gravity is relatively high. It can be applied to lower gravity reservoirs, but again, the optimal, the best conditions are listed here. All the other considered to be marginal before are also workable. In some of the Kansas oil fields, the depth and temp and pressure are not ideal, but you still can apply, and you still can do the partial miscible flood, because the miscibility does not. It's also a very kind of fluid term. It's a grayscale, so there's at some point where the miscibility starts. There's some point where miscibility is optimal, and in suboptimal regions, you still might have a very high recovery. So if we're talking, and again, I'm talking specifically for Kansas. For Kansas, it means if you could apply a CO2 EOR method, it means additional tax revenue for the state, and also, as you can see, the oil production is falling. There's been a history of recovering oil from Kansas reservoirs since early 1900s, even before that, in late 1800s. People were recovering oil in Kansas, but since about mid 50s to 60s, you see there's a decline in oil production, and the only method that can bring some production back is some kind of enhanced oil recovery, and one of the methods that is preferable, in my opinion, is CO2 enhanced oil recovery. And it has been calculated, all of those things were done before, but you can increase the production by about 28%, and potential revenue anywhere from 300 to 600. But actually, in current conditions of current situation, this number is quite higher. in a little bit different range. But there's a number of fields that could be done immediately. There's enough knowledge about those fields that there's modeling has been performed and so on and so forth. So basically, you can go ahead and do it now. But I will talk about some of the difficulties why it's not happening. Also, what you need to know about enhanced oil recovery. This method has been in use in the United States since about 70s, so it's nothing new here. There are a number of reservoirs that companies like Oxy or Kinder Morgan and others are flooding with CO2 with a high degree of success, especially at Permian Basin, but elsewhere as well. Denbury is another good example. And so this technology has been proven, has been around, and the only problem with this is that you need stable access to reasonably priced CO2. Also, oil recovery potential is important when you're considering a field that you want to flood with CO2 EOR. Again, one of the problems with let's say Kansas reservoirs is pooling, and it might be actually a concept that is not familiar to you because of the ownership of different fields. In Kansas and elsewhere in the United States, private citizens can own mineral resources or lease mineral resources for production. And that creates the possibility for your local businesses to actually enter oil and gas business, and that also means that you can lease a small piece of land to extract oil, and when you do this, your boundaries of your small piece do not end with the boundaries of the field, obviously, and because of all those different owners, it is very difficult to put them together, to bring them together, to actually do organized, combined, kind of cooperative type of effort on the flooding side. So as you can see here, there's a number of patches that where people do enhanced recovery with secondary method, which is water flood, and it is divided into those little squares because according to each lease that actually says that yes, we do have a water flood here. And so another, as I said, what enhances your potential for CO2 recovery is optimal conditions for CO2 flood. You also will be more successful. You have if you're close to CO2 source, and that creates a need for basic infrastructure and potential pipelines. And maybe you have seen this before. Maybe you have seen this Biden's, our president's plan to create an infrastructure. Part of this infrastructure is actually to create CO2 pipelines. And also, like I said, if operator is not interested in this capability, and if there are many operators who are not willing to do this, then you basically you cannot apply this in those certain areas. This is another example of how some of those fields look like. As you can see there, those different colors show you and those different squares show you where the water flood is happening and where it is not happening. And those divisions on the map state, that your mom and pop companies that actually produce oil in those different various fields. And in order to be successful, it is better to have a plan for the large field and apply your CO2 to certain zones that you created before. So it's a complex process, engineering process that requires a lot of coordination. And if you cannot do this coordination, then your CO2 flood is not gonna happen. But we know it works in Kansas, as you can see on this picture down here. We get, when we did inject CO2 in one of the our carbonate fields in Wellington carbonate field, we got enhanced recovery. This field was on basically is currently on the last leg of water flooding. It is producing very little incremental oil, but if you do inject CO2, you get oil cuts that are actually exceed 30%. It could be quite higher than that. And so, in order to do this water flood, obviously you need your to have your kind of ducks in a row. You can obviously do it without any preparation, but without any preparation, you might see or might not see the results. Also, it will kind of tell you if your investment is worthwhile. So that's why reservoir characterization is not required, but very much suggested in order to proceed with the CO2 EOR. And it is even more so applied towards CO2 EOR because investments are quite high. The needed capital cost to run the project, your initial investment is quite high due to all the equipment and preparations in the field. And so you need to understand where your CO2 will go. Well logging program, coring program, 3D seismic, formation fluid analysis, all of this needs to be done. Here's an example of some of the core that we recovered. We looked at compared to the well logs, all the different things that we as reservoir engineers and geologists do to characterize the field. So we took this fresh core, we correlated with the logs, looked at the fin sections, looked at the mineralogy, looked at if CO2 would or not interact with the rock in the reservoir and how it will interact, looked at relative permeability curves and so on and so forth. Did a preliminary well testing, and I would definitely suggest well testing to understand some of the features of the reservoir, how wells are connected, where you would expect your CO2 to show up, because in carbonates, as you might know, it is not a straightforward process. You have a lot of features that are kind of hidden. You might not see them on seismic, not necessarily. If you combine the methods, if you combine the seismic with well testing, with advanced well logging, you might actually see some of the additional things that might escape your vision before. And so in our case, we have this kind of larger feature going through the field, and that affected the flow. So, for example, if you inject the CO2 in this injector, the CO2 shows up in those two wells before it shows it way ahead of it showing up across that feature. And also the recovery here was quite higher than if you compare it to the wells on the east side of the fault. And so those things matter, and those things matter, and so you'll understand your reservoir better if you do have your well testing program done. Seismic as well is very important. Again, if you understand that you might have a feature, seismic will tell you where the feature is, what kind of feature it is. In our case, it was a progradation of some of the faulting. Then you build your reservoir models. You include those features and everything else. You update those reservoir models from before. In our case, it was an update, and we included those some of the features that we saw on seismic, and also could sense with the well testing from before. And then we could predict the flood a lot better. You do your fluid analysis, capillary pressure, relative permeability. You include it in your reservoir modeling. and reservoir modeling is performed to understand the, what is the economic forecast, and also optimize the strategy for the flood, and in order how to direct your flood, and how to stage it, and so on and so forth, and where the CO2 is predicted to move, and if it is predicted to move in the places where it is sort of unexpected, you can combine it with the water flooding methods to create certain curtains to contain the CO2, to increase the efficiency so it doesn't escape all across the field. So you need to be basically prepared very well before you start your CO2 flood, because CO2 is expensive. You don't want to lose it, and also you want to optimize your recovery, because again, CO2 is expensive and everything else around it is expensive. So you need to think through your strategy. In our case, this is how it looked like, again, because we actually had to apply some of the containment. So this is why you see this tight CO2 plume in the reservoir. Obviously, you see that your CO2 and oil are getting to the injectors, rather than escaping all across the field and in unknown directions, and according to the the preferred orientation of more kind of higher permeability streaks. So you expect your production to increase, and you model it again. You can model it more precisely if you do know your field better, and you can expect what kind of feedback you'll have across the time. And now we'll get to the second part of the presentation. I will be talking about the sustainability trend and investments in ESG. So we'll see that EOR is not the only component in CCUS. There's also storage, and this sustainable investment trend, and the investments are coming in this sector more and more. You will see that there's a place for this, at least in the United States, maybe other countries as well. So there are different methods of how people actually accommodate this concept, and again, this concept is applied to clean up your fossil fuel generation, power generation capacities, things like coal or natural gas or ethanol or fertilizers or cement or steel manufacturing. They all emit CO2, and in order to decrease those emissions, you can capture those emissions and store them underground. There's a mechanism right now for the pace for this. For example, in the EU there are carbon credits, and we can talk about carbon credits and at some separate time how they work, but basically it's important to know that there's a price that could be paid for the CO2 that you capture and also sequester underground. And if you can prove that you sequester the CO2, you can basically trade those credits across the nations. There's also increased need in power generation, different kinds of power generation. This is a price trend for the ethanol, but as you can see, the commodity prices but also including energy production prices are increasing due to certain events that are unfolding right now in my home country, for example. And with that comes more interest in actually making those production trends more sustainable with less CO2 production into the atmosphere. There's a number of CO2 facilities all across the globe. I encourage you to visit Global CCS Institute to see various reports that they produce. They do an excellent job. This is the status of 2019. Since that time, this graph is a lot busier, and there's a lot more projects that are actually coming online. all over the world, you see both the enhanced oil recovery, but for example, in the United States, there is a trend. Almost 70% of projects right now are actually storage and not CO2 EOR projects. There's the technical scope for CCS is predicted to only grow over time. So there's a, if you're looking at this graph and including on, and if we are talking about, next several years, you'll see that the need for CO2 storage is gonna increase, and there's a number of different industries that will need this help to get rid of CO2. It's gas to liquids and coal power plants, cement and methanol production. Everything you see on this graph basically is a go, and we're talking about gigatons of CO2 that need to be captured and stored, and that creates a lot of opportunities for businesses to enter in this space. And in the United States, at least in mid-continent region, and at least in Kansas, this is why it makes sense to do CCS. So you have large point sources of CO2, and if they're competing with renewables. Right now, Kansas, for example, producing. I'm not gonna say exactly the number, but it's around 50% of power production is coming from wind, renewable source. And so with this competition, coal power plants and others, they're costly investments. They can be just decommissioned. They need to be either retrofit, or we need to do something about them to keep them going. And personally, I would hate to junk those. It would be wasteful in my mind to junk those investments. And with mature oil and gas industry, and also with mature waste disposal industry in the United States, it doesn't make sense that if we don't use CCS, actually it might be a lot cheaper than all other methods of energy production that requires removing CO2 from the stream, meaning from fossil fuels. So here's this energy production profile, and currently renewables are playing higher role in all across the United States, but in this case in Kansas, definitely. Also, we know from recent events, in this case it was a bomb cyclone, the cold front that hit eastern part of the United States, and as a result, the National Energy Technology Laboratory in the United States has produced a report that basically says, look, if you want sustainable energy production, you need coal and you need nuclear. And if you want to make sure that your coal continues operating and it is sustainable, you need to think about how to do that. And CCS could be your answer. Yes, it is quite expensive. It could be expensive. The prices are coming down. They can be as low as $35, or maybe even less than $35 in current conditions. When I worked on a number of projects, several years ago, these were the prices for different facilities. And the reason I'm bringing up this slide is that you don't have kind of the magic number for CO2 capture. You can't produce it because different facilities operate differently. They have different designs. They have different schemes. They do have different availability of water, on-site additional generation capacity, power generation capacities, and so on and so forth. And so the price for the same power plant for different units could be different. And so you need to spec your plants accordingly and not underestimate it, and just know that it is impossible to pin out exactly what is going to be the price for each facility. Let's say, okay, if it's coal, it's supposed to be 60. Well, no, it could be actually a lot less, or it could be a lot more, depending on what kind of plant it is and what kind of design it is. So it's a very important part. There's also hydrogen that is coming online, so it's not only kind of old sources that need CO2. There are things that are up and coming, and hydrogen, especially if it's what is called now blue hydrogen, or things that you where you produce hydrogen from fossil fuels like natural gas, things like ethane, methane, whatever else. There are different components that you can use and produce hydrogen. But if you do it with the fossil fuels, then you need to store your CO2 somewhere. Yeah. And so there are, for site selection, before you can proceed and store your CO2 somewhere, you need to know something about your geology, and the commercial scale facility, a large scale facility, at least how the Department of Energy identifies it, it's about 50 million tons per year. But actually, you can do a lot smaller facilities as well. Nothing wrong with that, but the demand for CO2 storage, the larger the facility, the better your economics would be. Also, certain depth, as I said before, there should be a trapping structure. At least that's what I would prefer to have, because you'll not be dealing with the CO2 escaping somewhere. There's certain formation salinity. This is at least in the United States, this is a requirement from the regulatory agencies. And there are also some soft requirements as well. So you'll have things like availability of stack storage. That would be a preferable thing. But also things like public perception in that particular region and everywhere. But in particular region is very important, because your community where you plan to store CO2 might be against it for whatever reasons, and you need to be able to persuade them to that this is a good thing, or they will probably not follow along, and you'll not be able to do the project. There's also things like induced seismicity, and you'll see a little bit later why it is important to look at those. So again, how you're scoping your project depends. You start big, you start to understand where you are within a basin, and gather all the data that is available. Understand what your sites are, understand what your what your depths, what's in our case, for example, it was important to see what's the proximity to basement and what the basement structures do for this particular environment, because in our case we need to consider induced seismicity. You also look at what is your pressure head. In our case, again, in case of Kansas, most of the reservoirs, especially in the western part of the state, are under pressure, and so you can squeeze a lot of CO2 in those reservoirs. In other places, it might not be the case, and so you need to understand your environment. And as I said, salinity is important, and so salinity maps come handy. You also need to understand your proximity to sources, and what you can do about if your sources are not where your sinks are. And in our case, the sinks are far away from where the sources are. There are some sinks next to the promising sites that we characterized and know it is possible to do CO2, but there are some sources, like in this eastern part of the state, where you hardly find any CO2 storage sites and possibilities. So you do your due diligence, you understand your reservoir, and understanding a reservoir is for CO2 sequestration is very important. You understand, where your windows are to be efficient when you store it, to save money. You understand the structure of the reservoir kind of on a large scale as well. You take a core, you well logs, you understand, your structures, where your permeabilities are, and how the CO2 behaves in the reservoir. In our case, it was very important, for example, to look at the geochemistry of various strata points, just to understand that if you inject the CO2, it's not gonna penetrate the ceiling unit, and it's not gonna overflow into the formations above. You also look at the geomechanics, also to understand if what kind of fracturing there is, and what you can expect from CO2 taking off in those structures in all directions. Again, taking a look at the seismic and deriving some of the properties from seismic is important. In our case, it was for porosity, for example, that we could derive from seismic, but also various features that you see on seismic is highlighted there. It's very important. When you put it all in a geologic model, you create geologic model, and then you try to understand how it's going to behave, how your CO2 plume is going to behave there. This is kind of how the CO2 plume behaves in our case. And so if you take this Arbuckle reservoir, you understand that your lowest part of your reservoir will be the most receptive. Also, we looked at kind of grander scheme and a grander picture to understand, what would it take to actually inject CO2 on a large scale, meaning not only 1-2 projects, but the entire state. And we understand that you actually can run out of space, and it is very real. You'll overpressurize the reservoir, and there are all sorts of issues that come with this overpressurization. But we also understood that you can, in our area, theoretically, you can store more than 4 gigatons of CO2, and it's quite a large capacity. Some individual sites you can store, anywhere from 220 to 270 megatons at some of the sites. But if you start a large scale deployment, there is large potential to do this. But again, you need to be careful and not to overpressurize your formation in order to make sure that you don't have induced seismicity. And induced seismicity we do have, and this is again became a large problem for the oil recovery for the people who try to produce from Mississippian lime. It's a tight formation with high water cuts, and they try to inject water into all across the Arbuckle. So because of that, we started seeing seismic events. And this is where the monitoring on site comes handy to understand if you're causing the CO2, by injecting CO2, if you're causing the earthquake or not. And this is one of the areas where this Mississippian lime developments were happening, and this is where the earthquakes were very prevalent and continue to this day. And you can see on this radar image how the birds are actually flying out when the earthquake of 4.9 happened in this region. So this is the trajectory of how the earthquakes were happening throughout this development of the Mississippian lime. Right now it is not as active, and so you see the earthquakes are subsiding because there's less injection happening in those regions, but also because of some other things that I will talk about. And so with a lot of water going underground, because these in this map shows all the wells that inject water, different types of water, different types of waste too. So some of those orange circles, these are waste injection sites that sometimes inject hazardous waste or municipal waste or things of that matter, and they inject a lot of fluid. You also see a lot of oil and gas wells that are in blue, and they also inject a lot of water because of the high water cuts. And if you start injecting those higher amounts of fluids, higher at least than before, you start seeing the increase in pressure building up, and increase in pressure and increase in water levels rising, so that you might run out of space basically if you inject too much. And this is the pressure transition. We had the pressure transducer sitting at the bottom of the well, recording pressure for basically a couple of years, and we saw that progression as people were injecting water into the wells nearby. And with that came regulatory actions, and the decreases on injection capacities, injection volumes were stated. And so with that, we did have this is you see this is a number of earthquakes from before and earthquakes after the order became relevant came into place, and this is where the earthquake activity actually started to subside with less water injected in this area. And so with that, we if we decide to inject CO2, we need to understand that the water and other uses of the aquifer need to be taken into account, your neighbors. And so with that, you need to make sure that you adjust where you place your sites and not place them where your neighbors are injecting. Also, there's a regulatory framework that needs to be developed for CCUS, and that poses the additional challenge. There's needs to be understanding for both the pipelines and the pore space. Who owns the pore space and what are the procedures for this ownership? Who is liable for CO2 once it gets underground? That needs to be worked out as well. And public outreach is one of those areas that you need to work hard in order to make sure that your projects actually can move forward. With that, I don't have conclusions for the slide. It's just an overview and just some of the points that you might find interesting, and I'm happy to take any questions.
Engineer Eugene, thank you so much for sharing such great experience in carbon capture, utilization, and storage. I'm now waiting for your questions. Please, if you have a question, send it in the chat area, and I will read it out loud so that our instructor answer it. So the first question from Juice is saying, any examples of using 4D seismic and for monitoring injection in Kansas?
Well, for the seismic, as I said, you use, and it's a very useful tool to make sure that you understand your reservoir, where your features are, what are the faults, how they are oriented, how they're stressed. You can partially decipher from seismic. Of course, seismic is very important. And it is widely used everywhere on all CO2 storage projects. It's not exclusive. It's very similar to what you see in oil and gas development.
Awesome. Another question from Abdullah is asking, what are the challenges that carbon capture, utilization, and storage is facing? We always hear that these technologies are expensive. Why they are expensive? So he is asking for both for two things. He's asking what are the challenges and why the CCS is expensive.
So expensive is a challenge too. So I'll start with expensive, and we'll get to others. So mainly the main expense in all this is the main expense is it comes from CO2 capture. So CO2 capture is continuing to be expensive, but the costs are actually dropping dramatically. So for CO2 capture from a coal power plant, several years ago, on average it could cost anywhere from, I don't know, $80 to $120 per ton of CO2. It was just several years ago. Now the prices came down to about $25 to $45 per ton, and so efficiencies increase, and designs for capturing units and optimization is in place, and so you see prices drop. It's always like this. Any sort of technology is starting as very expensive, and the prices decrease with development in those technologies. It's the same with solar panels, the same with wind generation, and so on and so forth. So it was also for some of the oil and gas developments also were expensive at some point of time. especially offshore.
Great. Another question.
Challenges. I'm sorry. Yeah, challenges as well. So the challenges are many. But at the same time, you see that the projects are actually coming online, and every day you hear that people are permitting wells. So in our neck of the wood, in the United States, it's the price you pay for regulations. So the regulations are necessary in order to make sure that what you do, is technologically advanced enough so that you don't cause any damage to the environment, to the your neighboring users of the same space that where you try to do the project. And I think it's a good thing. At the same time, places could be overregulated, and again, for the good reason, but it often comes with the technologies that are not understood yet, or not common, where you don't have a lot of experience doing those things. But as people get more and more accustomed to those projects, I think the regulations will get to set in a place where they're not causing challenge for the site to proceed. So, and it is already becoming like this in the United States. So that one of the challenges is regulation. Another challenge is infrastructure. You need infrastructure to make sure that you get your CO2 from capture points to your sites. And this is the biggest expense, and a lot of times one company cannot do this infrastructure package. So you need multiple players to make sure that they play together and come together to create an infrastructure. And in this case, government will subsidize some of this infrastructure, because you can argue that this is a common good if you actually sequester CO2. As another challenge is that if you do inject large quantities of CO2, the induced seismicity could become a challenge, depending on where you inject your CO2. So you need to be careful. There are others, but these are kind of the main ones that come to mind, at least at the moment.
Another question. What do you do with CO2 that goes up to the surface?
Well, there's a procedure like with any sort of pollutant, because you inject other things in underground, and you have pollution that happens underground. There are certain procedures on how you can mitigate that. That being said, there's also oil and gas plays. There's a lot of leakages happening in oil, and especially gas plays, where you do have gas leakage into the reservoirs. And so there are mitigation strategies that you can apply from the oil and gas industry to mitigate those CO2 leakage. And I'm not gonna say that CO2 leakage is not gonna occur, but if you do things right, the percentage of sites that will leak is going to be, it's not going to be high.
So regarding the leakage and the corrosion, what actions taken to overcome the corrosion in the existing wells?
Well, you can look it up at the EPA and Environmental Protection Agency, United States Environmental Protection Agencies. What are the specifications for steel and cement? There's a special type of cement, special type of steel that you apply. Take a look at the EPA's website. They basically list the requirements for steel and cement. There are certain types of cement, certain types of steel that are doing well in presence of CO2. And the pH, low pH that it creates in the downhole is not a problem for those kind of materials, at least not on foreseeable future. So there are ways to mitigate that. Also, once you're done with the project, certain plugging procedure needs to be in place, and so again, certain cement, certain other materials that are used for plugging the well. There are lots of patents are coming up right now on how you do it more efficiently, and people are thinking about those things. So again, we can make it the entire lecture about this. I'm just not going to go into details at the moment.
Okay, we will take one more question as we are restricted by time. How effective is our CO2 capture nowadays? And he's also asking about the average daily capacity on a planet.
On the planet, like the globe, we're not very efficient on the global scale yet.
I think he's asking on a planet, one of the planets for CO2 capture.
I got it.
Not the planet.
Yeah. Okay, no, for plants, it's a good question, because actually, in order to be efficient with CO2, you can, theoretically, you can run the plant on sort of 100% capacity, where you use all the CO2 that plant emits. But the problem that you can run into is that you will need to build additional generation capacity for the plant to capture all of the CO2, and it can be done. It's not that it cannot be done, but the price could be very high, and so you can do 80% of the plant for capturing capacity. So you capture 80% of CO2, and then the price actually comes down quite a bit, and so it is still better than emitting 100% of CO2 into the atmosphere. So instead of emitting 12, like in this particular plant, the picture you're looking at, this plant emits anywhere from 10 to 12 million tons of CO2 per year. So it will emit 8 to 9 million tons of CO2 per year. I think it's a good strategy.
Yeah. I agree to you. Thanks a lot, Engineer Eugene, for your time and for sharing such amazing experience with us. Also, thanks for all the attendees that joined us today. We hope to see you all in the upcoming webinars and courses. I also hope that we meet the 2050 plan for reaching zero CO2 emissions. So thanks a lot all for attending. And last note, I will send all the links for the course registration and for the certificate also attending in the chat right now. Thanks again, and see you soon.
Thank you.